Welcome to this talk on GPT-4 ethics, where we unpack practical challenges and pathways for responsible deployment. Over the next slides, we will explore core tensions, bias propagation, privacy and liability concerns, and concrete operational steps teams can take to translate ethical principles into everyday practice. Think of this as a pragmatic roadmap to keep powerful models aligned with human values and regulatory expectations. This slide maps 4 dominant fault lines in AI ethics that practitioners face in real projects. First, authorship versus automation questions: who owns creative output? Second, fairness versus encoded bias highlights how skewed data produces unfair results. Third, transparency versus black box scale forces trade-offs between explainability and complexity. Fourth, accountability versus diffuse responsibility asks who is liable when autonomous systems fail. Spotting these tensions early helps design guardrails before scaling. This diagram shows how bias moves from raw training corpora into deployed models, so the problem starts long before release. Underrepresented groups, skewed labels, and toxic text propagate through token probabilities into data, annotation, and deployment biases. The takeaway is that fairness requires proactive interventions across the whole life cycle, not just post hoc fixes, because early decisions shape downstream harms and feedback loops. This tactical framework offers practical steps teams can embed into each sprint to reduce bias. Start with curated, counterbalanced datasets to diversify sampling and remove stereotypes. Use fairness-aware fine-tuning to penalize biased outputs and optimize equity metrics. Add human-in-the-loop review for contextual judgments and expert feedback. Finally, implement continuous post-market monitoring with automated alerts and iterative model updates based on real-world performance. This slide highlights data ingestion and consent gaps that create regulatory exposure, especially when models train on vast web-scraped content. Personal identifiers, medical phrases, and copyrighted text can end up in training pipelines without explicit consent, raising GDPR and CCPA risks like the right to be forgotten and fines. The diagram also notes potential investigations, audits, and class action exposure when sensitive snippets are regurgitated, so rigorous data governance is essential. Here we outline technical and organizational strategies to reduce data leakage and protect privacy. On the technical side, differential privacy adds noise to obscure individual points, synthetic data substitutes artificial datasets, and robust red teaming tests model vulnerabilities. Organizational best practices include data provenance logs to trace origins, opt-out portals for users, and clear retention schedules to define when data should be deleted, turning compliance into a competitive strength. Liability around GPT-4 errors is complex because responsibility is often splintered across developers, deployers, and end users. Emerging legal theories include product liability for design flaws, negligence for breaches of duty in development, and fiduciary duty in sensitive domains. Actionable responses are explicit risk allocation contracts that define roles and documented audit trails to preserve records of model decisions and human oversight, which together reduce legal uncertainty. Demystifying AI outputs builds transparency and trust through concrete tools. Chain of thought prompting reveals the model's reasoning path. Attention heat maps visualize where the model focused and surface key data points, and retrieval attribution layers link outputs back to source documents for factual verification. These techniques empower stakeholders to contest decisions, satisfy regulators, and protect proprietary model assets while sustaining public confidence in AI systems. When GPT-4 touches learning and professional work, it raises integrity challenges that require careful policy design. The model can blur authorship, tempt plagiarism, and short-circuit critical thinking by prioritizing output over analysis. To preserve learning outcomes while benefiting from AI, institutions should reinforce honor codes, mandate AI disclosure policies, and redesign assessments to emphasize process and reasoning instead of final products, keeping education and professional standards intact. For high-stakes diagnostic suggestions, embedding ethical principles in prompts and workflows is critical. The slide shows a loop where GPT-4 inputs are processed with autonomy, non-maleficence, and beneficence in mind, and then routed to clinician sign-off, so the system functions as decision support rather than a silent decision-maker. This human-in-the-loop design reduces malpractice exposure and ensures rigorous oversight when outcomes carry life or death weight. Translating principles into practice requires an end-to-end ethics program that operationalizes governance into measurable workflows. Start with strategic oversight and model cards to document intent and limitations. Convene cross-functional review boards for diverse perspectives. Then implement operational validation through daily workflows, KPIs, and whistleblower channels. Finally, use staged rollout gates and feedback loops for continuous monitoring, so ethical safeguards travel with the model into production. This structured approach to operationalizing AI ethics breaks the work into phases to make it manageable and repeatable. Phase 1 focuses on assessment and planning with ethical risk assessments and an inventory of use cases. Phase 2 runs proactive testing and red team drills while budgeting for audits and bounties. Phase 3 embeds continuous improvement through feedback loops and drift monitoring, all aimed at achieving human-centric AI that amplifies rather than undermines human values.